In this lesson, we're not going to go into the details of how energy and what types of energies are going to be. For that, you can go back to O levels and search my videos for work power energy. You will find different sources of energy and the rest of the things that are required for the basics of this chapter. We're going to go towards only specifically going to discuss the topics that are related to A levels physics only. And we will learn how to solve questions and what are the common questions going to look like, what the examiner expects from you if you are dealing with this chapter at least. So concept of work, we know that work done is force into distance, but we need to understand what force into distance should be. This is as basic as O levels. So it says that whatever direction of force is being applied, the distance should also be covered in the same direction. Now this idea will be used extensively in A levels at least, and to put you into plain perspective, a simple understanding of this also comes out as this one. For example, if an object is being dragged along by the surface or along the surface at an angle of, let's say, 20 degrees with a force of 100 newtons, and it is moving, for example, or it is going to move a distance of 50 meters, then find the work done. What will be the value of work done? So we know that the work done, for the work done, F and D should be in the same direction, or they're supposed to be found in the same direction. So the component along the x-axis will be responsible for the work done. So we need to find out the component of 100 newtons in the direction of the distance covered. So that will be simply 100 cos of 20. Now notice that there is another component in the upwards direction, that is 100 sine of 20. That is not going to cause work done because the distance is being covered in this direction. So only 100 cos 20 will be involved in this. So this will be 100 cos of 20 multiplied by, please be advised, use brackets so that the calculator does not confuse this angle with this one, and you can find your answer in joules. Then we have principle of conservation of energy. For this, I'm going to relate the efficiency of the system as well. The principle of conservation of energy states that whatever energy you invest in a system, it does not matter what is the outcome of the system, there will always be actually two outputs of any system. For that, I'm going to simply discuss the output of, for example, a heater, an electric heater, and a light bulb that we have in our houses. So both demand on the input, they're both demanding electrical energy from you. You provide them with electrical energy, and as a result, they will perform a function for you, or this machine is going to do a job for you. So the first output that we observe for any system is going to be called as the useful output. Now be advised that the outputs are of two types. First is useful, and the second output will be referred to as the wasted output. Why do we call this as wasted output? Because this machine was not designed to do this job. It was not its intended purpose. So output will be of two types, output 1, output 2. Every machine has that, right? So it's your job to categorize which one of this output is actually going to be useful and which one of them is going to be wasted for this system. Now, if we look closely, the light bulb that we have in our houses is actually giving us the energy of light. So light will be its useful output. But if you look at its wasted output, we can very clearly and sometimes generally feel that if you get your hand close to the light bulb, or if you ever experience changing the light bulb, you will experience that it gets quite hot. It heats up quite a bit. So it begs the question, did you design the light bulb to produce heat? No, you designed it to produce light. So the intended purpose was producing light. So anything other than that, anything, either sound, either thermal, either heat, anything else is going to be categorized as wasted energy. So over here, we're going to write down heat or thermal energy as wasted. Over here, the useful output of the heater is basically heat. It's basically thermal energy. You designed the heater to produce heat, but you may have noticed that in winters, when you run an electric heater or even a gas heater, at maximum power or at full power, it actually glows. It glows orange sometimes. So we can say that it is actually giving us light energy at that point. Did you design the heater for the light? No, you designed it for heat. So every system in the universe has two outputs. One of them is useful, one of them is wasted. It's your job to look at the machine and decide which one is useful and which one is going to be wasted. So based on this idea, we have the formula for efficiency. What students generally write down for the efficiency is simply they write down output over input multiplied by 100. This is incomplete definition. This is wrong. Why? Because there is one letter that's missing in this definition. Why? Because if you're talking about output, then you have to specify which output you're talking about. Are you talking about useful or are you talking about wasted? So efficiency is about useful output. What did you do, or why did you design this machine? What job was the machine going to perform for you? Divided by the total input. What have you invested? What did you give the machine to do for you? For example, if you have invested or if you have given this machine, let's say 100 joules of electrical energy, and it only gives you back 70 joules of light energy, then most definitely 30 joules have been wasted. Now, this idea that we have, that whatever we have invested will be accounted for. How? Some of it is in the useful output and some of it has been in the wasted category. So if you add them together, 30 plus 70, you still get 100 joules. This authority or this idea has been given to us by the law of conservation of energy. What does this tell you? Conservation of energy actually gives you the authority that one energy will be converted to another. For example, over here, electrical is being converted to light and heat. It will be converted to other formats, but it will never be the case that it is unaccounted for. For example, it's never going to happen in this way that you invest, for example, 200 joules in a system. Let's say you give 200 joules of energy and the system does work for you. And let's say that the output heat energy is 150 joules and the light energy is only 30 joules. Because if you add them together, you only get 180 joules, which is not what you provided it for. So there is 20 joules that is missing, that is unaccounted for. Law of conservation of energy says this will never happen. If the total is 180 and it's not equal to 200, that means that you have some energy, that you have something that you have not accounted for. You haven't looked close enough. So there will always be some 20 joules either in the case of wasted energy or either in the case of useful energy. Energy will land somewhere, either useful, either wasted. It's not possible that it lands in another world or another situation where it is not be seen or not to be found. It's not going to be possible. So this idea actually comes from law of conservation of energy. And basically every question that we do in work, power, energy actually stems from this idea, that is for the efficiency question. Okay. All right. So we have done pretty much first 3 to 4 points. Then we talk about power. So power is equal to work done divided by time. And I generally introduce another formula to the student, that is energy divided by time. Why? Because work done has a unit of joules per second and energy also has joules divided by seconds for time. So if both are the same quantities, then we can use both of them in the same formula. It doesn't matter. Okay. Plus work done is when the machine has done some job for you already, and energy will be generally considered as before the machine has done something for you. So over here, I can say that I have provided electrical energy, and I can say that the light bulb has done work for me and has given me back light as work done's product or the output of work done. Okay. So we have understood this idea as well. We understood point number 5 as well. We have point number 6 as well, as work done divided by time. Then we have power equals to F into V. You have to prove this, how this formula actually comes into being. Very simply put. So let's say that we have P equals to, power is equal to work done divided by time. We know from physics that work done is F into D. So what we do is we simply replace F multiplied by D divided by time. Now, if upon close inspection, we realize that if you divide this D by T, or if you divide or separate them D by T, then you're left with F multiplied by D by T. So what is distance divided by time? Distance divided by time is actually velocity. So you're left with the formula Fv. So the formula becomes power equals to Fv, which is mentioned in the formula over here. So we are done with point number 7. But let's discuss this formula. What does that mean? What is the meaning of this formula? Because this will be used extensively, very extensively in almost every question in this chapter. So power is equal to Fv basically means that if an object wants to continue its motion at a certain constant velocity, listen closely, if an object wants to continue its journey at a constant velocity, then it has to overcome, for example, it has to overcome a friction force or a certain friction force. And to do this job, the engine of that vehicle has to develop certain power. Okay. Now, why did I say friction force? You will see in some questions it's actually driving force. It is actually the force in the forward direction. It does not matter, because if we are talking about constant velocity, according to Newton's second law, which is F equals to ma, Constant velocity means that the acceleration is zero, which means F, the resultant force, is equal to zero, which means that the pulling force on the object and the stopping force on the object, the driving force and the friction force, they're both equal. If it is pulled by 1000 newtons of force, and that friction force is also 1000, which is why it does not matter if in the question is friction or if in the question it's driving force, it will still be used at F, because we know that the velocity is constant, the acceleration is zero, both values are constant, forward and backwards, right? So again, I repeat my statement. To maintain a speed of velocity v, the engine needs to generate a power of P to overcome the resistive forces of value F. And this is what we do in daily life as well. If the car is moving, let's say at a constant speed of 60 and 70, or 70 or 80, let's say, then it is experiencing a certain drag. So the engine has to provide that work done or that extra energy to the system so that it can overcome the drag or the work done required for the drag, right? That's how it maintains a constant speed. So we understand this point number 7 as well. Then we have potential energy and kinetic energy. We generally do this in O levels as well, but I'm going to do this over here again. He says that use work done is equal to force into distance to derive the formula for mgh. Now, very simply put, if you look closely, from one surface to another, for example, from the Earth, if this is an object of mass m, then its weight is mg. You need to provide a force of mg in the opposite direction so that at least it starts moving in the upward direction. So if you're providing the force in the upward direction, the force is going to be against weight and its value should be mg. And it is going to cover the distance in this direction, which generally comes out as height h. So upon close expansion, we can see that F into d, basically the force that you applied was actually the weight, which is mg. And the distance that you've covered in the direction of the applied force in the upward direction is actually the height. So you come to the formula of mgh. Now, the second formula that we have is the kinetic energy formula. You will have to perform the algebra on your own. I'm just going to mention the starting points. Then you're going to go with questions. So it says that we know that the work done is F into d, right? And if you write down this in terms of kinematics equation, then we have, in place of F, we have ma dot s, as F equals to ma. Then we have an equation v square is equal to u square plus 2as. And if you make s the subject of the formula, this equation becomes v square minus u square divided by 2a. Now, to place this over here, you get ma v square minus u square divided by 2a. He says that the initial velocity is 0 because we're starting from this point. So this actually cancels out and we are left with that a cancels out. So what we are left with is 1 over 2 mv square. Since this is work done and the work done has been done to move the object, so this becomes kinetic energy. Let's move to the questions. We have first, we have the question for kinetic energy. It says that the energy increases by 4. So what has happened to speed? Now notice what's the relationship between kinetic energy and velocity. Velocity is being squared. So if the kinetic energy has increased 4 times, then what has happened to the velocity? So you take the under root on the other side, you take the under root, proportional v, so the velocity comes out as 2, which means that if the velocity has doubled, or has been increased by double the factor, only then you can see a factor of 4 velocity of increase. You can see that on the other way around as well. If you put, let's say, half m v square, and then you put 1 over 2 m into 2v whole square, then this will become 4v square. So initially it was 1, now it is 2, giving you 4 times the kinetic energy. So this question is plausible and this option is right. Question number 16 suggests that there is a force of 90 newtons pulling it forward. 90 newtons pulling it forward, and there is a drag force of 50 newtons pulling it backward. So we are left with a surplus force of 40 newtons in this direction. What is the gain in kinetic energy when it moves through a 6 meters? So we have established this idea from this proof that the work done to move the box eventually becomes the kinetic energy of the system. So we're simply going to write this down as work done being equal to kinetic energy, and the work done has been done by extra 40 newtons of force multiplied by a distance of 6 meters. This answer comes out very easily as 240 joules. If you want to pursue this question in detail, what you can do is find out the F equals to ma, find out the acceleration, then equate it to half mv squared, then find the velocity, and then put this, then cancel out the mass, and then go for the velocity and whatnot, right? So I would suggest that employ the law of conservation of energy and think about it in this way. That extra 40 newtons of force, if applied for 6 meters, if it continues to apply for 6 meters, what will you end up doing? You will end up injecting 240 joules of energy extra into the system, and that will eventually become half mv square, or that will become a part of the kinetic energy. So no matter what you look at it, it's going to be option A. Then we move to question number 7. Again, this is where we're going to use the formula P equals to FV. So notice carefully what he mentions. He mentions that there is a resistive force of 180 and he's moving at a constant speed and generating a power of 3 meters and moves a distance of this much amount, right? So how do you find this? Now, the resistive force and the driving force will be equal because the speed is constant. So what we find out as P equals to FV, the power is 3 kilowatts, so this will be 3000 watts. F is 180 and this is V. V comes out as a fractional answer, so that will be 16.6 meter per second. Now, since we want to find time, what we can do is simply use the formula speed equals to distance over time. So speed equal to distance over time, we are supposed to find time. So we have the distance, which is 4 kilometers. So speed is already given to you, which is this one. So this will be 16.67 equals to 4,000 meters, 4 kilometers. And this is T. So T comes out as 240 seconds approximately. So this will be your answer for this question. Okay, moving on to the next question. Again, this is one of the confusing questions. And keep in mind, always keep in mind that whatever direction of force is, if the distance is covered in the same direction, then the work done will be F into D. Simply put, the angles will not be involved. So he says that there is a constant force of 9,000 newtons parallel to the inclined plane. Body has a weight of 20,000 newtons. It moves 40 meters along the plane and at a constant speed, which means that the forward force and the backward force will be equal. The body gains a height of 12 meters as shown. How much work has been done, dissipated as heat? Now, this is a good question. What has happened is that you have invested energy in the system this way, that you have applied a force to move along this point. So you have actually ended up at this location. And how much energy have you invested? So energy invested as work done, which is work done, equals to F into D. How much force have you applied? You've applied 9,000 and you move for a distance of 40 meters. So 9,000 multiplied by 4 meters gives you an answer of 306,000 or 100,000 joules. I'm going to write this down as 360 kilojoules to shorten the number. Now, he says what has been dissipated as heat, which means that something extra has been done in the system. This is the first suspect that you should, look forward to, that something is wrong, something is not right. So what has happened, he's mentioned you the weight and he's mentioned you the height. So what we have done, what we've observed is that it has gained some gravitational potential energy by moving from this point to this point. There is an extra added energy into the system as mgh. So what you have done, you've invested 360 rupees, $360, 360 kilojoules into the system, and it has manifested itself into two things. First, it has gained some height, and second, there must have been some friction with the box. So that extra energy has been used in that to overcome the friction. So that is what he's asking you. So let's find out the energy converted. Now notice I'm changing the word. First I used invested, now I'm using converted, because whatever you have invested is going to get converted into two things. So energy converted in gravitational potential energy will be equal to mgh. Now notice one more problem over here. Please keep your eyes open. This is kilonewtons, which means that mg has already been calculated for you. So this is going to be 20,000 multiplied by height that you've gained is 12 meters in this scenario. So 12 meters, this is going to come out as 240 kilojoules, of course, right? Please note that mg is weight and weight is represented in newtons. This is weight, not mass. If it had been mass, then I would have multiplied g with it. This has already been done for you. So this is mg and this is h. So you spent $360, let's say $240 have been successfully converted into gaining height. What's the remaining energy that cannot be found? So we subtract 360 kilojoules from 240 and we realize 120 kilojoules are nowhere to be found. Where have they went? Where have they gone? So they have been converted into heat by doing work against friction. So this is what he was asking you, right? Okay. And if you have to find the force of friction, that could be found by work done equals to F into D. You lost 120,000 joules. F is what was the friction that you worked against, multiplied by how long did you move with that friction. You moved to 40 meters. So you put 40. Now you can find the force of friction that actually had to be overcome while this motion was happening. Just another second part of another question. Question number 16, again, similar idea, similar attitude. He says, you can pause the video to see the question. I'm going to directly solve it. He says, what is the work done moving the barrel a distance of 5 meters up the slope? So in this question, what we can see over here is that this force is not known. We don't know what that force is. But since he says that it is moving at a constant speed, I can guarantee that this upward force will be equal to this downward force. Now, the downward force is going to be found by the component of weight, which is already given to you over here with the angle of 30 degrees. So if I make the triangle of forces, this is my weight, which is 1000 newtons. This will be a component with the parallel, or you can say perpendicular to that component. And this is going to be another component over here. So we know that this angle is actually going to be the similar angle over here. So this is 30 degrees. So this will be mg cos of 30 degrees, and this will be mg sine of 30 degrees, the angle in front of the component. You can use trigonometry, or you can go back to watch the video of A1A vector components, and you'll see that how we make this triangle. Now notice that the only component responsible for pulling it down, if it was left to move freely, the only component responsible will be this component, this one, which is the component of slope of weight, right? Which came out as mg sine theta. So this is mg sine theta. So this will be equal to the driving force because it's moving at a constant speed. So now I need to find out the work done. So I can simply use work done is equal to F into D. I know the force now, which is mg sine of 20 multiplied by the distance moved up is 5. Let's put in the value. So this is 1000. Again, be advised, for God's sake, this is weight. This is mg already done for you. You don't have to multiply this with 9.8 again. So then we have a sine of 20 degrees. You multiply this, please, separately with 5. And the answer that you're going to get over here is going to be 2500. So option B will be your answer. Okay. All right. Then we have question number 14, very straightforward question. He's just trying to confuse you. Don't worry about that. He tells you that the force utilized by the object to move in a certain direction is going to be kv squared. Okay, fine, doesn't matter. He says, what is the relationship between P and V? No problem. We know that power is equal to force multiplied by velocity. So let's put force over here. So we have kv squared multiplied by V, that is a part of the formula, right? So what do we get? We get P equals to kv cubed. Now, we need to find what similar formula that we get. Now, since we see that everything is being subjected to K, let's make K the subject of the formula. So that is P divided by V cube. And that is option C. No problem. Even if you had located this equation, that you can clearly see that the only V cube that you see is in this equation, not in anyone else. Next question is just lengthy. It's lengthy, not tricky. Okay, just keep an eye on these words. This is 1000 newtons. And this is 1000 kg. Be careful. This is mg converted already. This one needs to be converted into mg. Be careful. Okay. So what he says that we have a crane system. It is moving at a constant speed of 10 meters per second. How much power needs to be generated? So the force of 1000 is for the hook. Now what is the hook? This is the hook of that crane that weighs, for example, 1000 newtons. That is its own weight. Okay. Then we have a mass of 1000 kg. This is 1000 kg that is being lifted upwards. So what's happening? The total mass, or if you will, total weight is actually 1000 plus this mg. So what does that become? So total mass, if you want to convert it to mass, you have to divide this by g. So the total mass becomes 1000 divided by 9.8. That is for this hook, plus 1000 kg already, which has been already converted or given to you as kg. So that is going to be the total mass. It doesn't matter wherever you go, whichever way you choose. Now he's asking you about the total power. Let's say this is given in the MCQs that everything is in kilowatts. The speed is given to you. So we are going to use the formula P equals to force into velocity. The idea still, if it is moving constant speed or with constant speed upwards, then the upward forces and all the downward forces are equal to each other, which means that this mass that I've calculated, be advised, this mass has to be multiplied by g, so that this becomes weight, this becomes force, which will be placed here, and velocity is given to you, it will be placed here. So if you simply multiply this with 10 meters per second, you will straight away get your answer. Please don't make a mistake on the calculator. You get 5500, which is 5.5 kilowatts of power. Again, we move to the next question. This question requires diagram for complete understanding. So I'm exaggerating that the angle is 30 degrees. I know that 30 degrees may not look like this much, but it is going to, I will exaggerate it so that we understand it. It says that a train has 200 people, 70 kg average mass, and the 80,000 kg mass of the train itself. How much power does the engine need to produce if it is 40% efficient and is moving at a speed of 6 meters per second? So first we are going to calculate the power actually needed by the train to maintain this, which is going to be found by FV. And we know for in this situation that if the velocity is constant, then the forward force is equal to the backward force. So let's find out the backward force. We know that the total mass of the system is actually this much, and this is mg, the component of weight. And what is the total mass of the system? So we have 80,000 kg of the train plus 200 people averaged mass at 70. So this is that mass that we have. And then we have to multiply this with 9.81 to get the component of weight. Okay. Then we make that vector triangle that we have over here. That is going to be one component, and this angle will be same. This is going to be 30 degrees. And then we are going to make this one component which is responsible for everything. This is that component that is responsible for at least pulling the train downwards. But if the train is going uphill, that means that the backward force, which is mg sine theta, this component is mg sine theta, this component is mg cos theta, not our requirement right now. So mg sine theta is equal to this mg sine theta because it's moving at a constant speed. That means the forces are equal, as I've said this before. Moving at a constant speed of 6 meters per second. So let's calculate this. So we have mg, which is 80,000 plus 200 multiplied by 70. For God's sake, please put a bracket over here so that you can calculate the mass properly. 9.81, this is the force. Then we have sine of 30 degrees. Now this whole bracket is basically force that is along the plane. And then the velocity we have as 6 meters per second, which is 6. Now this is the power required by the system. So basically this is the output of my system. I need this much power, or you can say PO. I need this much power from the train, no matter what happens. So whatever train takes as the input is not my problem. I need this much output under all circumstances. So what I've calculated is basically my power output. And the efficiency is given as 40%. 40% efficiency. It says what is the actual power of the energy of the engine. Now be advised, the engine needs to be much more powerful than the power that you have calculated. Why? Because if engine gives 100 joules, only 40 joules will go forward and 60 joules will be wasted. That is what the efficiency means, right? So I will treat this as my output power and I will divide this with 0.4 because the formula that I have is efficiency, which is 0.4 equals to output over input. Of course, I'm not writing useful and total because I'm running out of space. So the output power that you've calculated is this one, and you want to find the input power. So input power goes to this side according to the formula. So what you're left with is input power is equal to output divided by 0.4. So when you divide this whole expression with 0.4, you will find out what the power of the train's engine should be. So this comes out as option C, 6.9 kilowatts. Again, engine will provide 69 or 6.9 megawatts of power. Out of that, 40% will be utilized to take the train upwards and 60% is being wasted. So it's quite plausible that the engine is going to come out to be much more powerful than the actual power requirement that we found by using this formula. Okay, we'll have to invest more than required because it's not 100% efficient. Again, similar, exactly the same question as we've done before. He says, what's the useful power of the output, useful power of the engine? We have angle, and of course, we're going to make the components. This is the weight component. This is the normal reaction. This is the component of weight. How much weight or how much backward force is actually there? So there is a component of mg sine theta plus W by 5, which is given as a resistive force. Right? So what we're supposed to do at this point is be careful. I'm going to solve this in one step. So we need FV. The constant speed is already given to you, 15 meters per second. So I'm going to put 15 meters per second first because that is just one factor. Now F is the problem. Figuring out F is the main issue. So force is actually what is acting downwards. So first let's write that down. We have the mass of the train is 11,000 kg. So what we have is 11,000 mg, right? So 11,000 multiplied by 9.81 to make this mg sine theta. So this will be sine of 10 degrees, probably, yes. So 10 degrees, this is one force plus W by 5, weight divided by 5. So that will be 1100 multiplied by 9.81 divided by 5. This is that W by 5 factor that we're putting over here. Now this whole will be divided. No need to divide this because this is the exact answer that we require. So what you can do is find this separately and find this separately, then add them together and then multiply it by the velocity which I've already written in the front. So this comes out as 60,000 watts, which is going to be 60 kilowatts. So this will be your answer. Don't make a calculator error. If you don't like this single step method, you can solve this one by one, does not matter. Solve this separately, then add them together, then multiply by 15, you will get this answer. Question number 18, we have an object entering at 28 meters per second. So what's happening is that a car actually moves like this. So a car has a velocity of 28 meters per second at this point. What is the velocity at this point if it gains a height of, for example, 22 meters? That is the question. Okay, so most definitely, if the engine is providing constant power, if it's not providing extra power, then most definitely this velocity will be less because some of the energy will have gone into the mgh conversion. So if the change in gravitational potential energy has been equal to the change in kinetic energy, let's replace the formulas. One common misconception over here is that the mass of the car or the object is not given, does not matter, it's okay. So mgh equals to 1 over 2 mv square. Now notice what has happened. Mass gets cancelled out from both sides. Okay, fine. So let's take this 2 over there. So what are we left with? We are left with 2 into g, which is 9.81, h, which is 22 meters. This is what the height it gained was, equals to v square. So I know that the final speed is going to be less than the initial speed, than 28. So I'm going to write down 28 square minus v square. Now, if this is confusing again, please notice that if there is a change in kinetic energy, what you can do is v square minus u square. If you don't understand this, then look at this way. Final kinetic energy minus initial kinetic energy. So if you take 1 over 2 common over here, you're left with this one, and then this difference of squares. For God's sake, please don't do it this way. That if a speed changes from 28 to, let's say, 20, don't take 28 minus 20 and then 8 square. This is wrong. You can try this on the calculator. 28 square minus 20 square is not equal to 8 square. You have to take the squares separately and then subtract them. So I've done that over here. When you find the velocity in this situation, this is going to come out as 18.77 something. That is option B. Okay, please don't make an algebraic mistake. Now, this question is interesting in terms of pure understanding. So what's actually happening? Try to understand that there is a difference of weight. So if the system is in equilibrium, that means otherwise this should have moved downward. This should have moved upwards. If that's not happening, that means that one of the forces is coming from the electric motor's rotation. And how much force that must be? So the force is actually going to be the deficit or the difference of both of them, which is 50 minus 20. So the electric motor is providing a force of 30 newtons under some circumstances or under the circumstances so that it does not leave or does not move from its position. And most definitely it's rotating this way so that it can dominate this weight or it can provide help to this weight so that it stays in this position. We need to find the power of the motor. So power is equal to force into velocity. We figured out the force, but we don't understand the velocity of the movement of this motor. We don't know what it is. So we go back to the circumference of 0.5. What does that mean? So if I look at the circumference of this disk, it looks like that if this is the disk, let's consider this to be the starting point. Let's say this is my 50 newtons and let's say this is my 20 newtons. If the disk is rotating, which is mentioned, rotating at 20 revolutions per second, it means that it is moving 20 times in this direction. So 20 revs in 1 second. And we know that one revolution is 0.5 meters. How? Because that's a circumference. Circumference means the total length of path. So the total length of this circle is actually 0.5, which of course has been found by 2 pi r. If we had done 2 pi r, we would get 0.5 meters as its circumference. So I know the distance and I know how many times it's rotating. So I know how much distance it is covering per unit time. So it is completing this loop 20 times in 1 second. So I can say that 20 times covered a distance of 0.5 meters in a time of 1 second. So what has this become? This is actually distance divided by time, which becomes velocity. So we have to select this cleverly, right? So we have to be clever about this. This is 30 multiplied by 20 into 0.5 divided by 1 second. So this comes out as 300 watts, which is going to be option A. Now we move towards this question. This is again one of the difficult questions that has proven very difficult for the students to be visualized. But let's discuss this in a more simpler way. So he says that there is a conveyor belt, for example. Now we understand that a conveyor belt is going to look like this. We have some rollers on it, and let's say that the conveyor belt is moving in this direction. So we have a chimney, let's say. We have a chimney system that is dropping some sand, or let's say some mass on this trailer. So this trailer eventually moves and carries the sand away from this, or carries the mass away from this. Okay. He says, what is the extra power needed to support this? If there was no mass before, now there is some mass over here. So most definitely we need to provide some extra energy, some extra power to do this job successfully, or complete this task successfully. So to understand this, we go towards this idea. Again, since we're dealing with power, power is equal to force into velocity, right? So he says that the conveyor belt already has a velocity v. Now notice that the sand, when it eventually falls on the belt, it has no velocity. Although it has velocity, but it's in the downward direction. What is the final velocity? It's in the right direction. So we can say that the x-axis component of the velocity before it falls on the ground is 0, but now it has some value. Okay, so we know that the change in kinetic energy, or the change in energy of the system, will be started from 0 and lands at Vx. Now force we have done in physics as rate of change of momentum divided by time multiplied by the velocity. Okay, so if we have to discuss the change in momentum, what has happened to this mass of sand that is falling? Its momentum has changed. Previously that momentum was 0 along the x-axis, of course, in the forward direction. Previously it only had the momentum in the y-axis direction. Now it is in the x-axis direction. So you can say the initial momentum was 0. The final momentum looks like mv, and since this mass is being spent as m kg per second, I can also put the time over here as 1. This comes out as my force as a change of momentum multiplied by v, which is already a part of the equation. So I am left with mv square. Of course, we are ignoring the negative sign over here. Does not matter. So the final answer is option D. In this case, the additional power required, apart from supporting the frictional losses and everything, will be mv square. So if you put more mass, you want it to move at a higher speed, then most definitely you need to provide more rotational energy through the electric motors to this conveyor belt. Okay. All right. So the main understanding of this question is this change in momentum from 0 to some value along the x-axis. It's falling downwards. It has y-axis momentum, but no x-axis momentum. The only component that it has is previously it's 0. Now it becomes mvx, because momentum is a vector quantity. So you have to deal it that way, that the downwards momentum or the upwards momentum will be dealt along the y-axis, forward and backward momentum dealt as x-axis momentum entirely separately from y-axis, just like projectile motion. Now we come to this question. Again, this question is a bit tricky for the students sometimes, because these questions are not generally discussed in these chapters. So no need to worry. Let's see what's happening. So it says that there is a dam, and the height of the dam is given to you at a height of 30 meters. So this is 30 meters away. The water falls up to 30 meters, and the water that is falling has a rate of 340 cubic meters per minute. The density of water is given. Now we know that the formula for power generally in this situation, since we are required to find power in all options, power is equal to work done divided by time, or energy divided by time. In this case, in a dam situation, it's always gravitational potential energy. So I know that this is going to be mgh divided by t. Now what do I do about this? Where do I find mass? I have density. So I find density is equal to mass over volume. I know the volume, which is 340 meter cube. I take it to the other side. So I get that the mass of the system is going to be density multiplied by volume. Density is 1000 given in the question. Volume is 340 multiplied by G, which is 9.81, and height, which is given to me as 30 meters above the surface. So this is going to be 30. But I'm still lacking this problem. Still, there is one problem. Where is the time t in this power equation? Where do I get that? So we have to pay attention to this unit, that is 340 meter cube per minute. So this per minute is actually the unit of time. So let me write this down again as open format. So power is equal to mgh divided by t. If I isolate this m divided by t over here and multiply this with gh, now it becomes very apparent, very simple to see where I can find this mass per unit volume, right? Or volume. So we had, instead of mass, we have written down density multiplied by volume multiplied by G multiplied by H divided by T. I can isolate the volume divided by T as the value given to you as volume per minute. So indirectly what I'm trying to say is that we already have time, which is 60 seconds. So let's put in the values. What we get is 1000 multiplied by the volume is 340 multiplied by G is 9.81 multiplied by height is 30 meters, divide by 60 seconds because this was given as per minute. And you can see this over here that this is actually mass per unit time. Sorry, volume per unit time, which is given to you over here, meter cube per minute. So you just have to adjust the values looking at the formula properly and correctly, and you get to the formula. Now, since the system is only 90% efficient, that means whatever energy water carries, let's say if the water carries 100 joules, it only give you back 90 joules. So what I'm going to do at the end of all of this, you can find the power at the end of all of this. I will multiply this with 0.9 so that I can find out what power do I actually get at the end of the day. So this answer actually comes out as 1.5 megawatts. So this is my answer, right? Okay.